All right. I'm hoping that this will be our last video. Maybe. No, we already did this one. All right, so example 17.11. So here we have got a neuron can be modeled as a parallel plate capacitor. You biologists should appreciate this somewhat because it's talking about cell membranes and all that good stuff. And you can see that you've got these negative charges inside the cell and positive charges outside the cell, and it says to find the capacitance of a neuron and the number of ions required to establish a potential difference of 85 millivolts. Assume that the membrane has a dielectric constant of 3, a thickness of 10 nanometers, and an area of 1 times 10 to the negative 10th meters squared. So lots of information going on here. Okay, so let's go on over to the other slide and we can write some stuff down. So first, we were given that it had a potential difference or voltage of 85 millivolts. It has a dielectric constant of 3, thickness of 10 nanometers. So the distance is 10 nanometers. 10 times 10 to the negative 9th meters. This is 85 times 10 to the negative 3rd volts. And then it also told us the area, which was 1 times 10 to the negative 12th meters squared. All right, so this is first wanting us to find the capacitance. So the capacitance with a dielectric. So you got to have that weird looking kappa, which I just write K's the same way, unfortunately. Okay, so the dielectric that it gave was 3. Permittivity, the area was 1 times 10 to the negative 12th meters squared, divided by this distance, which was 10 times 10 to the negative 9th meters. Right, do the math of that, and you should get 2.66 times 10 to the negative 13th farads. Hopefully you guys come up with that. The next one that it showed, or the next question that it actually asked in that slide was, it says to find the capacitance and the number of ions. So what you do for that part, it's not really a part A, B, but I'm making it part A and B, I guess, is that we are looking for the amount of ions. So we found the capacitance, and are we given a voltage in here? We are. So we could actually find the charge. Okay, so if we take our capacitance that we found, and we take our voltage that we're given here, and we solve, we should get 2.26 times 10 to the negative 14th coulombs. Now, that is not giving you the amount of ions. So ions you would do divided by 1.602 times 10 to the negative 19th coulombs per ion, which then cancels out those coulombs, the same way that you would find how many electrons. So 1.4 times 10 to the 5th ions. Okay, so that's example 1711. All right, section 17.7, energy stored in a capacitor. So you take this battery, you plug it up, you can put charges, positive charges on one plate, negative charges on another plate. So the energy stored in a capacitor is the work done by the battery to separate the charges, essentially. And so energy stored in a capacitor, so suppose we look at this process that says at some point of time when one plate has positive charges, the other has negative, and then the potential difference between the plates is this voltage. So voltage is equal to the charge divided by the capacitance. Okay, that's our equation. That's this equation, essentially. All right, they're just using the little q instead, and they're rearranging that equation. So if q is small, then you could also show the potential energy is charge times voltage. That was an equation that we had before as well. Okay, so potential energy is equal to 1/2 times the base times height. That gets into a little bit of calculus. If we were in calculus-based physics right now, we would talk about how this was like an integral. But really, I'm not going to do anything like that. I just want you to see that this is a voltage versus a charge graph, okay? So in order to find this potential energy, you could do the area under this curve, which is just a triangle. So it's just 1/2 base times height. So 1/2 Q times V. All right, so let's look at an example really quick. And this will be, we're almost done. All right, so fibrillation is the chaotic pattern of heart activity that's ineffective at pumping blood. So you've got this device known as a defibrillator. I don't think I said that right. Is used to shock the heart back to a normal beat. It charges a capacitor through paddles on the skin so that some of the charge flows through the heart. Obviously, it could be very dangerous to, put too much. And this is saying if an 11 microfarad capacitor is charged to 6 kilovolts and then discharged through paddles into the patient's body, how much energy is stored in the capacitor? Okay, and then it wants us to figure out how much charge. So let's do part A first. So energy is stored, so that's the potential energy, okay? And we know that that is 1/2. It told us in this previous one that it was 1/2 times the charge times voltage. Okay, but if you look back through the problem, I guess we should write what we were given. It gave us that we had a capacitance of 11 microfarads, and it gave us a voltage of 6 kilovolts. Okay, so are we given capacitance in this equation right here? No. So we need to figure out how to get capacitance in there because that's the information that we're given. So just remember here that charge is equal to capacitance times voltage. So now let's plug that in to that Q right there. So we have 1/2 capacitance times voltage times volts, which is just 1/2 capacitance times voltage squared. Okay, that's all it does. So now we can plug into that equation. All right, so we've got 1/2 times our 11 times 10 to the negative 6 farads times our voltage, which is 6 times 10 to the third volts squared. And we should get 198 joules. Okay, remember that potential energy is measured in joules. And then that was part A. Now for part B, it says how much charge flows through the body if the capacitor discharges completely. So now this is just wanting us to find the charge. Okay, so we are given, we have both capacitance and voltage in this first one. So we have 11 times 10 to the negative 6th farads times the voltage, which is 6 times 10 to the third volts, which is 0.06 coulombs. Or you could say 6.6 times 10 to the negative second coulombs. Or you could say 66 microcoulombs. However you want to go about it. Okay. Hopefully that all is kind of coming together. I know it's a lot of equations, and I know that it says some words that are just, electricity is just hard. It is so hard because it's so hard to imagine. Okay, it's kind of like chemistry in that aspect. All right, so energy stored in electric field. So potential energy is energy of the interaction or field energy. So the energy stored in a capacitor is stored in the electric field between the plates. And we can use the energy stored in the capacitor and then calculate how much electric field there is even. And how much energy per unit volume is stored. So we've got a few more equations, and then this is actually the last slide. So in a parallel plate capacitor, the energy stored, so we've got the potential energy is 1/2 times the capacitance times the voltage squared. Or you could break it down a little bit further than that. You could say 1/2 times, and now capacitance is equal to, now if we were talking about that had a dielectric in it. Okay, so I could take that and I could plug it in for that C times voltage squared. Okay, so stick with me for a minute. Now remember that voltage was equal to electric field times distance. So now if I take that and plug it in there, so let's go down here and say, okay, potential energy is 1/2 times K times the permittivity constant times the area divided by distance times electric field times distance, and that's squared. So then I can hear you guys through the screen kind of. So you've got electric field squared times distance squared divided by distance. Well, what happens to this distance on the bottom then? It cancels with one of those. So you end up with this essentially. I hope I don't think I need to rewrite that for you guys. And then energy density is the electric potential per unit volume. So that is this little U, so which is equal to the potential energy divided by the area times the distance. So area times distance, that would be like meters squared times meters, which would be meters cubed, which is volume. Okay, so energy density. So we've got 1/2 K permittivity times area times electric field squared times distance, almost forgot that, divided by the area times distance. What happens to the area? It cancels. What happens to the distance? It cancels. So the energy density is actually 1/2 K times the permittivity constant times the electric field squared. I really wish that it did have an example so I could show you how that applies. I apologize. But that is the end of our PowerPoint here that seemed to take forever. I think it was like 70 some slides. So, I know it's a lot, but we're almost